The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Our next speaker, I know, has worked with Professor Wires through ACI for many, many years, and I've also had the pleasure of serving with her on some ACI committees. Expert in materials science, always a delight, and she's going to be talking to us about her topic, evaluation of the proposed European rapid screening test for stainless steel reinforcing bars. So I'd like to introduce Carolyn Hansson from University of Waterloo. Thank you, Carolyn.
Thank you, Michael. Well, first of all, I'd like to say that this is a great honor to be here at the symposium honoring Richard Wires. We've had great fun over the years, haven't we, Richard? Arguing, not always against each other, but arguing together with other people too. So it's been very good. So the last presentation talked about corrosion-resistant reinforcing steel, and if any of you have ever worked on these steels, you know that it's very difficult because we want the steels to last 100 years. But of course, the departments and ministries of transportation want the results in a couple of years. And so getting the stuff to corrode is what we're all about. Everybody else wants it to not corrode. We want it to corrode. So one of the problems we have is getting it to corrode in the time that a student has to finish a master's or a PhD. And different set of goals. So if we look at how you evaluate and rank corrosion-resistant rebar, if you do conventional testing of rebar embedded in concrete, it'll take several years. If you test them in synthetic pore solution and add incremental amounts of chloride, it still takes several months. The ASTM has two tests. One of them is the cracked beam test. This is a 60-week test. And the A955 rapid macrocell test, which is done in pore solution, that takes 15 weeks. So the canny Europeans have come up with another suggestion. There's a test that's being used in the European Union to evaluate the effect of admixtures on the corrosion of black rebar in concrete. And Schoening and Ramstrom in 2011 proposed that this be modified slightly to be able to do a very rapid screening test of steels. The reason being that more and more companies are producing different grades of stainless steel, and of course the departments of transportation are asking, which steel should we use? What's the most cost effective? If we use the lower grade, is it going to last for the length of time? And so on and so forth. I know we're at any rate under pressure from Hannah Shell over there at the Ministry of Transportation. When are you going to give us these answers? So this is one of the tests. What Schoening and Ramstrom suggested was we do 10 replicates of each steel, not always practical, that the stainless steel be cast into what they call a standardized mortar cylinder. It's the standardized mortar, not the standardized cylinder, which is a European mortar standard, with a water to cement ratio of 0.5, and they add 4% chloride by mass of cement as sodium chloride to the mixing water, so it's admixed in the original concrete. And after 24 hours of curing in the mold, cylinders are immersed in a saturated calcium hydroxide solution to prevent leaching from the concrete. And then the open circuit potential, half cell potential, is measured for 24 hours, and then a potential of plus 200 millivolts with respect to the saturated calomel electrode is applied to the steel, and the corrosion resulting from that is monitored. And if the pass-fail criterion that they're suggesting is that if the current goes over 0.025 milliamps per square centimetre for more than 2 hours, it's considered to have failed. So we questioned some of the parameters in this, and this is the experimental setup just to show you. Steel. This is the steel embedded in concrete. This is a circular counter electrode, which in the case of Schoening and Randstrom was platinum. We can't afford platinum. We're using titanium mesh, iridium oxide coated titanium mesh, and we're sitting it in calcium hydroxide. There's a reference electrode, and it's all attached to a potentiostat. And you'll notice there's a small cover on this, by the way. There's about a 25 millimeter cover, so it's not very big. So the questions we have. First of all, is plus 200 millivolts versus saturated calomel the most appropriate potential to apply? And I'll show you why we don't think it is. Is 4% sodium chloride appropriate for the admixed? Chloride as sodium chloride. Is this corrosion limit the most suitable for screening these steels? And does the concrete mix design or mortar mix design influence the results? And the most important question, of course, do the rankings of the different steels from these tests, this test, correlate or correspond to those from more conventional tests? So this is what we set out to determine. Well, first of all, the potential. For those of you who are not familiar with corrosion testing, this is the anodic part of a cyclic corrosion curve where we're applying a potential. This is the half cell potential, and these are six different steels. The steels are identified down here, all stainless steels. And you can see that the half cell potential varies from about minus 260 millivolts to plus 20 millivolts. So there's quite a range of half cell potentials, but we're applying a potential of plus 200, which is here. The other thing to note on this is that this plus 200, it corresponds, or this dashed line here, corresponds to the maximum level of the corrosion rate. This is the corrosion current density on a log scale. And below this it's slightly less, and above it's slightly less, so this is the maximum level. So is that the appropriate point? The reason I've drawn in this dashed line here is because this represents the equilibrium potential in a pH of 13 for the oxygen evolution reaction. Potentials below this, oxygen reduction, the reduction of dissolved oxygen in the pore solution of the concrete, is the cathodic reaction, corresponding to the dissolution of iron as the anodic, or chromium or whatever, as the anodic reaction. If you go above that line, that cathodic reaction is not thermodynamically possible, and oxygen is, in fact, the reaction goes the other way and oxygen is involved. So we question this, in fact. So our modifications of this procedure that we're presenting today are as follows. We only did 3 replicates of each steel because we only have 5 potentiostats. So we had 5 steels, measured, cast the concrete so they're all in the same concrete, measured them, then repeated the process for the next 3 weeks, because it must be nice to work for a stainless steel company where you have a lot more equipment than we poor academics have. We also decided it was better to use a typical highway concrete mixture, because we don't want to know what the ranking is in a mortar with 0.5% water, the water to cement ratio. We want to know what the ranking is in the type of concrete that's used in Ontario in highway bridges. The major difference from this was that we used a 12.5 maximum aggregate size because of the minimum cover that we have. And we had a water to cement ratio of 0.4. And we had 3 different test variables, which are shown in the next slide. We started out with a potential of 200 as represented or as recommended by the Europeans. And we then tested also 100 millivolts. The chloride content, we started out with 5%. Now you may think that's very high, but that is in fact the highest level that we found reported in practice from field concrete in Canada. And so it's pretty high. And then we tried 3%. And the concrete mix, we used a 75% general use or type 1 or OPC, and 25% slag, and then the second one we used 100% of the Portland cement. And these are the data we got from the 25% slag mix, 5% chlorides at 200 millivolts. And 4 of the 5 steels immediately started to corrode. The only one that didn't was the UNS 2205 down here, which didn't corrode at all. So we decided there was no point in repeating that with replicates, so we decided to cut down the chloride level. So the next slide is showing ones with exactly the same mix up here, except that it's got 3% chloride instead of 5%. And these are the 3 different quotes, unquotes, replicas. And you can see they're all over the place. If you look at this orangey coloured one here, which is the XM28 or S24100, it's got the highest one here, it's got the lowest one here, and it's the highest one here. The only one that was consistent throughout was that at 2205, which is this one here, this one, and this one. And otherwise, it's a lot of scatter. And we believe that scatter is due to the fact that you're on the cusp of the cathodic reaction for oxygen. So we went down to 100 millivolts. But again, we got a lot of scatter. In the first one test we did, none of them hit this. Oh, sorry, this is the line of the criterion proposed by Schoening and Randstrom, above which it's a failure, below which it isn't. And you can see none of these failed in this case, none of them failed in this case, and there's just the 2304 that's just peaking above that at this level in this one. So this was with 100 millivolts and 3% chloride and with slag. The next set we did was without the slag, and otherwise, again, 3% chlorides and 100 millivolts potential. And you can see that none of them hit the line up here. All of them are well below. There's a lot of scatter, but they're all well below. These are very similar. This one's suddenly got a little bit of increase, but nowhere near this maximum level. So the next thing we did, by the way, those 2 gentlemen over there who did this work. So they're the ones that we have to thank for all of this. Tim Bandura and Colin van Neerhuis. So what the next thing they did was break the stuff open. This is where they enjoy it, hammering the concrete open. So, and we looked at the surfaces to see if we could see any corrosion and see if there was any correspondence of the corrosion we observe with what we see on the electrochemical tests. And to give you an idea of what our ranking was, this is a 2304 without any observable corrosion. This is the same alloy at a different test, and you can see what we describe as a little corrosion. And this is a 316LN, which has got a massive amount of corrosion on it. And in the next slides, we have circles, this one, for example, which is the UNS 316 by 31653 or 316LN, depending on which scale you're talking about. The little circles mean there's a little bit of corrosion. The medium circles means there's a medium amount, and this means there's a large amount. This one corresponds to this specimen down here, down at the bottom. So these are all of the data from all of the different tests, and you'll see none of these corroded and these ones did. And these 3 showed corrosion even though they're well below this pass-fail line. 24100, all of the ones below didn't corrode. The ones above this line did show corrosion. The 2101, LDX 2101, they had one of them below the line and the other 2 above. These did not corrode at all. And this is the 2205, which showed no corrosion in any system. And this is the 2304, which showed 3 specimens corroding below the failure line and the other ones not. So to put this in a summary, here we have what we call the ranking for this test. So the data outside the parenthesis is from the visual observations. So for 3 replicates of each. So in this case, for example, if we looked at this 31653, we had corrosion on 2 of the 3 bars, but it didn't go above that, excuse me, above that pass-fail line in the electrochemical tests with this one, with 200 millivolts. If we go to 100 millivolts, same thing. We have two specimens here showing corrosion. Only one of them passed the pass-fail line. In this case, we had two with corrosion, and none of them, and they didn't go above the pass-fail line. The interesting thing is, for the straight OPC, none of them corroded, either electrochemically determined or in visual examination. So the next thing we did was compare these rankings with the rankings of visual observations from long-term tests of the same steels, or steels from the same bars, cast into concrete. And in the second column, the first column is the data from the tests I've just shown. The second column is from bars cast into concrete, again the same concrete mix, with cracks induced mechanically longitudinal to the bar and above the bar and exposed to de-icing brine, a de-icing brine with 21% chloride, for about 18 months. And what you'll see is there's a complete correspondence. 2205 has the best ranking. The next one is the LDX 2101, and then the 316LN or 31653, and then the 24100 or the XM28, and then the 2304. For transverse cracks, they're slightly changed. These two have switched places, the 2205 and the 2101, and these two have switched places. But you'll notice that in all of these columns, the 316, which is regarded as the Rolls-Royce of stainless steels, is in fact number 3. The bottom row here is from poor solution tests, and it's a different criteria in this case, criterion, and that is it's an indication in ranking of the chloride content at which the first bar of 5 bars of each steel began to corrode. So the chloride threshold, but of course there's always a range of chloride thresholds. So this is the ranking from the first. This means it had the highest chloride threshold. This one had the lowest chloride threshold. And you can see there's a bit of a change. Again, 316 is number 3, 2205 is number 1, same as these two. But this one is different and has switched places with the 2304. So we conclude from this that the 200 millivolts saturated calomel is probably not a good potential to apply. And what we want to test in the future, and haven't done as yet, is instead of applying a fixed potential with respect to the reference electrode, we apply a fixed potential differential or polarization from the half cell potential up to a certain level. Because at the moment there's about a 250 millivolt difference in half cell potentials. So if we're applying, say, 200 potentials to one of them, we're applying 600 to another. So we want to test that with the same polarization level. The other question we have is whether that pass-fail is sufficiently severe, because you saw that we got corrosion on a number of specimens, but they did not, on the electrochemical tests, pass that line. Now remember, what we're measuring electrochemically is the average corrosion rate over the whole bar, and what we're seeing visually is corrosion over a small area. So it's difficult, because, unfortunately, until somebody makes transparent concrete, we can't correlate them very easily unless we do an autopsy. But what we feel is that an order of magnitude lower would be a conservative evaluation. And the other thing that really struck us was the difference in behavior when we did a straight OPC rather than slag. And there are two factors here. Slag is usually used because it does impede the diffusion of chlorides into the concrete, slows it down. But what we're seeing here is perhaps that it's not binding as much chloride, and of course it's known to decrease the pH somewhat. So those two factors mean that once we've got the chloride in there, it might be not as beneficial as it is in terms of the diffusion. But the most important conclusion, of course, is how is the ranking of these steels compared to longer term tests? And we found that on the basis of inspection, the tests, they actually ranked relatively well with the longer term tests. I think a lot more work is needed with some of the, manipulating some of these parameters, but it does look as though it's got some future. So on that, thank you very much.